So first of all, I want to thank everyone for inviting me to come and talk. My name is Christopher Liljenstolpe. I am the CTO and co-founder of a company called Tigera. Now, how many people, quite a few people who have used Kubernetes. How many people are familiar with a project called Project Calico, networking project in Calico? Yeah, I was the original architect for Project Calico. So that was sort of my brainchild a number of years ago. My background has been mainly large-scale systems environments, chief architected a number of big ISPs, global ISPs, and various bioinformatics companies, etc. So I've done sort of big systems for a while. Everyone's talking about how we're now automating the infrastructure. Some of us many years ago figured out quite some time ago that if you wanted to run a network of thousands and thousands of routers, you needed to A, make them simple, and B, automate the heck out of them. Otherwise, you end up hating life. So some of this is, for some of us, this is, we know this, we've been doing this for a while. It just moved into it's moved into more modern technologies. So about 16 months ago, we took Project Calico out of where it's originally homed and started up a small company called Tigera, got around to funding, $13 million, and we've been off the races since. So that's Tigera, that's me, and where we came from. What I want to talk to you a little bit today is about networking and network policy in this new kind of environment. And I'm going to focus sort of on Kubernetes, and that's where Tigera is primarily focusing on because that's where all the cool kids are right now. Right? But we do support OpenStack, we do support Mesos, Docker, and a number of other platforms. So, I'm just going to go through a real quick history lesson. It used to be you had racks of servers. Racks of servers were connected to the outside world. It was a very north-south data path. Everything followed physical cabling, and life was good. It was really simple. Along came the virtualization guys, and the idea was you had virtual servers now in racks, and now instead of following a physical path out of a rack and through a firewall into the outside world, your VMs could move around. They'd move around too often, but they did move around. So all of a sudden you had network paths in your infrastructure that ended up starting to become more east-west rather than north-south. So that starts causing slight issues, because now if I'm going to, just like almost in any other industry, in IT, we really like taking something we know that worked in one model and try and keep doing the same thing over and over again, even after it, the phrase, doctor, it hurts when I do that. Well, don't do that anymore. We tend to not take that advice. We just take the thing we started with and we keep on trying to flog it on and on. So what do we do to replicate that old legacy model in a VM world? Let's take a look. So an old enterprise network, bunch of servers, physical network, connectivity out, life is good. We probably need some kind of security. So we stick a firewall, and we basically say, these servers should go through a firewall to talk to these servers. The degenerate case is, we trust everything in the data center, and we just put a firewall on the outside, and anything inside the perimeter is obviously trustworthy. That worked so well for Sony, a certain credit reporting agency just recently. I'm not going to mention the name, so somebody won't bingo me. But that perimeter security model, we learned sort of doesn't work. You need to start providing some kind of isolation within the infrastructure. Well, in the legacy environment, that was really easy. Servers in this block need to talk to servers in that block. I'll just drop a firewall box in the middle. Well, now we come into virtualization. These VMs are no longer in a physical location. So how do I make these? How do I follow the same model? Because we like replicating the same model. I'm going to build a virtual Ethernet. So I'm going to build a VXLAN or a VLAN or whatever. And so I go over a physical layer, and I'm still going to stick the firewall there. So what this might mean, for example, is two servers need to talk to each other in the same rack, go 5 suite lines over to go through a firewall somewhere over there, and then get sent back potentially to exactly the same rack. But this sort of works. how many people have seen this kind of environment in their infrastructure? How many people have interesting issues with deploying applications that cross this kind of environment? So I worked for a large service provider in Australia who shall remain nameless to protect the guilty. And I was chief architect for the carrier, the service provider side of the business. The IT guy said, basically said, networking at scale, can you come and help? We're having problems deploying applications in our internal IT. So this is the carrier, the business, not the carrier being a service provider. And when I came in, sort of looked at their diagrams, there were places where there were 8 virtual firewalls, all doing NAT and DNS-ALG between one end of the app and the other. How many people think that will deploy right the first time? The second time? The 20th time? This worked to a fashion. Then we sort of came along and said, well, gee, VMs were good, but they're not dynamic enough. So now we want to do containers. Those VMs lasted weeks, months, maybe a couple of years, right? And you could have this virtual firewall, and that was sort of static. This VLAN talks to this VLAN. How many people here have firewall rules that no one's touched in 5 years because no one knows if they still are valid anymore? I'm sure everyone here has kept perfect hygiene, right? Yeah, exactly. So now, where I might have had thousands of VMs, now somebody comes along and says, I want to do Docker. And I've got this VM environment. I'm just going to put Docker. Your developers come along and put Docker containers on these VMs. Or Kubernetes pods now. So where you might have had thousands of VMs, you might have tens of thousands or hundreds of thousands of containers in your infrastructure now for reasonable container environments. And these things last much less than weeks or months, right? Some of these things might last minutes, days, hours, whatever. Your scaling example, that container came up, it might just go down a couple minutes later, right? So now, I now need to start, if I'm going to do the same segmentation model, I now need to start building overlays for the containers on top of the overlays for the VMs and run those all through the same firewall. And people know the turtle model, right? We just keep on building turtles. The other way we talk about this in the networking world, this is 1,500 bytes of header and 40 bytes of payload. So, so now you end up, to get from place to place, you might go through 4 or 5 stages of de-encapsulation, re-encapsulation, go through multiple stages of firewalls. How many people have seen this in their environment? How many people have tried to debug this at 3 o'clock in the morning? The thing that started Calico was I've troubleshot BGP networks, multi-continental BGP peering disagreements between multiple service providers in about 10 minutes. It took me a whole weekend to figure out why packets from here were ending up on VLAN 54 versus VLAN 47. And it's all of the stages of encap, re-encap, who's applying what policies where. This starts becoming really complex. At the end of the day, these things, how many people are running IPX or AppleTalk or NetBEUI in their infrastructure today? These are all IP, right? If these are all IP, we know how to get IP traffic around. There's this thing called routing. We have this little thing called the internet. I know it's new, but it's a good case example for networking at scale. So we know these are IP. We're not doing anything other than IP. Why are we building all these L2 adjacencies? Building virtual Ethernets to run things through firewalls in the middle, just to replicate a model that worked when you had servers that you racked for an application and that sat there for 10 years until the fans died. So we've just replicated a model multiple times. It doesn't make a lot of sense. Don't do this. So let's talk about Kubernetes. The nice thing about this, when we started pitching this model, and I pitched it to OpenStack folks, they said, oh, this is, you have to support L2 because there's 3% of the use cases might need to do broadcasts or something. It's like, yeah, it's a 3% at best, probably more like 0.3%. use case do you want to tax your entire infrastructure with a whole bunch of complexity to handle the really rare corner case? So we had lots of conversations in OpenStack, etc. Along came Kubernetes, and the guys at Google said, these things are just IP. We should just give them all the same IP, unique IP address, and it makes things much simpler. It's like, yeah, that's what we've been saying. So can Kubernetes show us how this works? Simplified networking model. You have pods. Pods connect maybe to an overlay, maybe not to an overlay. In Calico's case, we can just use the underlying physical network if you want. These are all its IP. Each of these things have an IP address. They're all connected together. That's great. We can just get rid of the overlay, actually. Now everything can talk to everything else. We're not going through middle boxes. We're not going through anything else, right? So this is now simple. This is called the public internet, right? This is IP routing. If you want to think of it, these connections, potentially these could be routers, i.e. servers running routing daemons. And these things are all just IP addresses being announced. Everyone knows where everything is. Everyone can talk to everything. That's great. Simple, easy. However, if somebody gets in, everything can talk to everything, right? So the original Kubernetes model, everything just has an IP address, and everything can talk to everything. It's great, simplifies things, but we do have this little problem here. Okay. So what we really want to do is say, we know, one of the nice things about this new cloud native model is we're trying to rewrite things into smaller, discrete components, call them microservices, containers, whatever you want. We sort of know that this thing doesn't have an infinite number of connections that I don't even know because the guy who wrote it got hit by a bus 10 years ago. We know this pod needs to talk to this service, needs to talk to a MySQL, or excuse me, a Postgres SQL server, and we know the basic connections. So we can start identifying which of these workloads need to talk to which other workloads. We can build a service graph of our applications. And the way we do this in Kubernetes is we can start applying labels. You saw a pod spec. One of the things you'll notice in the pod spec that you just saw a while ago is you can attach labels to these things. This is a Postgres server. This belongs to application 15. This is role dev. This is role prod. You can start attaching labels to these things that identify what they are, what functions they have. We can also start using namespaces. In Kubernetes and other things, you can start having namespaces. This thing belongs in a namespace. This thing belongs in a different namespace. It's a different container of pods, so to speak. So we can take namespaces and we can segregate them up, the pods up into the various namespaces, and we can start building these graphs where things in namespace A can only talk to things in namespace A. Things in namespace B can only talk to things in namespace B. You can also create a pod that talks between the two. Some pods might need to cross that boundary, others may not. You can then start getting finer grained. You can start saying that certain pods, user authentication or user front end needs to talk to a Postgres server. And then the Postgres server needs to talk to a logging environment or something along those lines. But the front end doesn't necessarily need to talk to that. You can start defining these by simply identifying what they are and the policies that allow you to connect between them. So here's a couple of examples. We have a very large SaaS provider, storage as a service provider, basically moved from VMs to Kubernetes on bare metal. Required to do test, dev, and prod isolation. Their design was physical firewall with multiple Kubernetes clusters. So this is what they had built. Test dev, let's say. Each had a different overlay network going through the firewall. Extra overlays, in-cap, de-in-cap, consumes performance issues. Also, it means that these servers, because this is a physical isolation here, are now isolated. If all of a sudden the blue workloads aren't being used at a certain point in time, those are stranded resources. Whereas the green workloads might be being used there. It'd be nice to be able to mix resources, not define, as you said, tying containers to specific resources. I want the resources to be fungible. So, what do we do instead? Run just a single cluster. Don't run separate Kubernetes clusters. Don't use an overlay. Give each test dev and production get a namespace, and then we have a network policy that says things within namespace are isolated, and define other policies within the namespace. So now, Kubernetes will just launch workloads wherever they need to go, wherever there's space, and you have a policy. And that policy says that this namespace, the name is production, and it has a network policy annotation that says, normally in production, I don't allow anything to talk to any container in production. And then you say, you have a network policy that says, if the namespace is production, then I'll allow traffic that matches labels of namespace production. So now I'm going to allow traffic within production to talk to production, but not allow to talk to anything else. 3-tier application. Large financial, standard 3-tier application. Again, they're using firewalls to isolate their tiers. So this is what they built. Firewalls, pods, connecting multiple tiers together. There's a lot of management overhead in this, because now I have to build special pods, each that have special connections to different overlays. It also means that if somebody gets lucky and lands on this, they can span all the things that that pod's connected to on both sides. How do we do this? Each tier gets a label. We don't use namespaces here. We use network policy to isolate that traffic and allow the traffic based on labels. And those labels only allow connections required for the application, and we get rid of the overlays. Yep. So again, same kind of image. And this is Kubernetes network policy. Calico is one thing that implements this. There are other folks that implement this. We can talk about how we do it, but the right policy here, again, network policy, tier front end is going to allow traffic on port 80. And then middle tier policy says anything that's labeled tier middle will allow traffic from tier front end. So front ends will allow traffic from anyone on port 80, and middle tier will only allow traffic from front ends. And then the database tier will only allow traffic on 6379 from middle tier. Now these labels are attached by Kubernetes to the pods. Wherever they show up in the infrastructure, these policies are rendered in real time. Talking a little bit about how Calico does this, you can have 100,000 pods across 1,000 servers. You can churn that environment 200 times a second, where you're inserting and starting up pods, pulling pods down, changing policies. 99% of the time, these policies will be updated across the infrastructure in less than 10 milliseconds. And for those of you we were talking about firewall rules being left in and people forgetting what they are, when the pods go away, the policies that were attached to those pods also go away. There's no cruft left behind. The policy is only rendered for the duration that that pod is in use. Bare metal services to containers. Large storage as a service provider again. Needed to provide best security across thousands of servers, and they eventually need to move their applications off the bare metal to containers. They had firewalls with tens of thousands of rules in the firewalls. They had custom automation rules to process all of these things, to assign subnets and address ranges to each application and build ACLs across all of the switches. When we talked to them, they ended up with a little problem. They were literally First of all, they had to automate these firewalls. Those aren't necessarily that fast. They had exhausted the TCAMs on most of their switches and firewalls. They were literally 6 months away from having to turn off new business because they couldn't add any more rules to the firewall infrastructure. And you go to Cisco or Juniper and say, can I have a bigger TCAM, please? They love that conversation. It's going to take them 3 years to give it to you, and you're going to pay for it dearly, right? So how do you deal with this? And the problem is, these firewalls have cross-product rules. They have rules that have all potential combinations of traffic because you don't know what's going to be coming through them. What we did, we put the same kind of labeling scheme in place, and we use that not only on containers, but on bare metal as well. So now, the firewall rules, and this is how this works in Kubernetes network policy and in Calico specifically, we put these filters, so if there's filters that relate to yellow workloads, we attach the filter right in front of each yellow workload. It doesn't go anywhere else. And it's in the compute node. Lots of memory. Pretty fast. Same thing for green, same things for blue. People talk about filtering being slow in the Linux kernel. We can put 16 million rules in front of a workload and we get no performance impact. Wonderful thing called IP sets. Don't use IP tables for large lists. Use hashes. They're much better. And this is the solution. Again, labels, match labels, who you're going to allow traffic from, who you're not going to allow traffic from. So that's the presentation. Reasonable amount of material to cover in a fairly short order.